Hello and welcome to Electronics with Emrys. This is a beginner's guide to resistors. If you want to skip the intro and get straight to the content, I'll put some timestamps up for you. Before we get started, I want to send a special thank you to Marian from Romania for joining my channel at the enthusiast level. I really appreciate you supporting the channel. As an enthusiast level member, Marian gets an immortalized thank you in a video, and more importantly, he gets guaranteed personalized help with his questions and projects from me via email. You can see more details about memberships by clicking the join button on my channel. I want to say now that I can't cover everything about resistors in this video. For one, I don't know everything. And for two, I think I could talk for hours about what I do know and you would be bored to death. Let's just stick to the things that are common and basic, and I'll let you do the research if you want to learn more about a specific area of resistors that I don't cover. Sound good? Let's get started. The absolute basics. These are both common schematic symbols for resistors, with the American standard symbol on the left and the international standard symbol on the right. Resistors are usually named with an R and a number, and their values are measured in ohms, represented by the Greek letter omega. If you see an arrow through a resistor in your schematic, it means that it's a variable resistor. There are many other variations, but I'm going to leave it to you to search for those if you're interested in seeing all the different types of resistors that are out there. There's quite a few. You can start by searching for the two standards that I have listed at the bottom of the screen. So we know generally what a resistor looks like in a schematic now, but what really is a resistor? A resistor is a conductor that has a linear voltage to current ratio. What exactly does that mean? Mathematically, it means that the voltage V of a resistor is going to be equal to the current I multiplied by some constant value, which we call resistance, R. This is one of the most important equations in electronics, and it's called Ohm's law. It's worth noting that we also have a name for the reciprocal of resistance, which we call conductance, usually denoted as G, but we're not going to really talk about that much in this video. It's just good for you to know that it exists at this point. We'll get into exact use cases later on, but for now you should know that Ohm's law works three different ways. You can use it to get a voltage from a known resistance and current. You can use it to get a current from a known resistance and voltage. And, maybe a little less obviously, you can also rearrange it to get a resistor value if you know what voltage and current are required in your circuit. There are two main types of resistors, fixed value and variable value. Fixed value resistors are by far the most common that you'll see and work with. They come in a lot of shapes and sizes, but the most common two are axial and surface mount. Axial resistors are also commonly called through-hole resistors because they're intended to mount on a circuit board by placing their legs through holes in the board. Surface mount resistors, as their name implies, are intended to be mounted onto PCBs, but more specifically, they are soldered directly to the surface of the PCB. These are the most common in modern electronics because they're small and low cost. But axial resistors are extremely useful for hobbyists because of how easy they are to work with. Regardless of how the resistor looks, it can come in a wide variety of values. These values are split up across decades of resistance equally depending on the tolerance of the resistor. For example, a 10% resistor will use the E12 series of values. These may seem like random numbers, but they actually are evenly spaced on a logarithmic scale so that there are no gaps for the selected tolerance. Just as an example, a 10% tolerant 6.8K resistor can be as large as 7.48K within tolerance, and the next value up, 8.2K, can be as small as 7.38K. If you want to get more accurate values, you have to move up to higher tolerance parts, which will have more values for each decade. When I say decade, I mean that the resistor values will have the same numerical value, but the power of 10 will change. For example, you can buy 10% resistors of 4.7 ohms, 47 ohms, 470 ohms, 4700 ohms, and up, even until as high as 4.7 gigaohms. For each power of 10, you'll get the same number of values between 1 and 10, and that number will be determined by the tolerance. The variable resistors come in a variety of types, mostly split up by how they vary. The most common one most hobbyists will encounter will be the potentiometer, which is a user-adjustable resistor that is very handy for tuning circuits. There are a lot of other types of variable resistors, ones that vary with humidity, pressure, distance, and probably any other variable you can think of. But to use them right, you need to know the math behind them. Let's move on to exactly what math you need to know to use resistors effectively in your designs. Resistor math. Ohm's law you just heard about in the basics section is worth repeating here. I don't think I can overstate its importance. If you go into electronics, you'll run into this equation over and over. It will just become second nature to you. I like to use this visualization of the equation because you can just cover up the value that you want to get, and that will give you the equation you need. For example, covering up R gives you V over I. Sometimes you'll need a value of resistor that's not exactly what's available, and you can get different values by combining resistors that you already have. One way to do this is by placing them in series. If you put two resistors in series, the values just add up, so the new resistance is just R1 plus R2. Another way to combine resistors is to put them in parallel. The parallel combination is a little bit more complicated. If you only have two resistors, it's easiest to use the equation R1 times R2 divided by R1 plus R2, or we often call this the product over the sum. If you have multiple resistors in parallel, then you can use the equation 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus as many other resistors you want as reciprocals. You add up all the reciprocals, which you may remember I mentioned were conductances. You add all these up, and then you take the reciprocal of that conductance value and you end up with the final resistance. You can also do series parallel combinations. So you could have a resistor R1 that's in series with a parallel combination of R2 and R3. And this is simplified by doing the parallel combination first and then just adding that result to the first resistor. There are two common configurations of three resistors that are worth mentioning. On the left, we have the T configuration of three resistors, which is also known as a Y configuration when it's drawn like this. Each resistor in the T or Y is named for the external node connected to it. On the right, we have the pi configuration, which is also known as a delta configuration. Each resistor in the pi or delta is named for the two external nodes connected to it. A T or Y configuration can be directly converted into a pi or delta configuration, and it happens enough that we have a set of equations to handle that easily. I don't expect you to remember these from this video, but it's good to know that this conversion exists, and I'd just like to point out that there's a lot of symmetry in these equations. So if you do need to use them, it can help to calculate those duplicated sections of the equation first, and just reuse that calculated value to speed up the conversion. I'll save the rest of the math for the specific applications of resistors. Common resistor packages. Resistors come in a lot of shapes and sizes, but I want to discuss the two most common, axial or through-hole, and surface mount. Axial resistors are the quintessential resistor. They have been around for a very long time and probably will continue to be around for a very, very long time. They commonly come in a variety of sizes, ranging from as small as 4 or 5 millimeters long all the way up to 50 or 60 millimeters long. Even with the same type and power ratings, there are variations in size, but the most common ones I use are 1/8 watt and about 7 millimeters long. If you want to know the value of a resistor just by looking at it, the big ones will just print directly on the resistor what the value is, but smaller ones will use a color code. There's an easy mnemonic to remember the order. Black bears ravage our young goats, but valiant guardians watch. Conveniently, the first word being black also means the first color is black, which corresponds to 0. After that, we just count up the digits. Brown, red, orange, yellow, green, blue, violet, gray, and white being 9. You might also notice that this is basically just Roy G. Biv with some added colors. But I found it hard to remember where white, gray, black, and brown went without the black bears coming to my rescue. In a 4-band resistor, usually one band will be separated from the other 3. That will be the tolerance band, and you'll start reading from the opposite end of the resistor. The first 2 digits are numerical for the resistor value. The third band is the power of 10 to multiply by, and then the last one being the tolerance will usually be a special color, with gold meaning 5% and silver meaning 10%. More accurate resistors will have more color bands, usually with 5 total. The first 3 being the numerical value, and then the multiplier and tolerance. For those, the tolerance is red for 2%, brown for 1%, and violet for 0.1%. DigiKey's got a pretty good calculator for resistor values on their site that you can use to easily figure out what the values are for common resistors. There are 6-band resistors and other tolerances out there, as well as other multipliers and even some that add a temperature coefficient band at the end. But those are much less common and outside the scope of this video. I'd recommend to use the almighty Google to find a good color code chart if you run into something you can't decipher from what I've told you today. Moving on to the surface mount versions, things get a little easier to understand, if not easier to actually read. Most SMD resistors will have the value printed directly on them in the format of 3 or 4 digits, with the last one being the power of 10 multiplier and the other digits being numerical values. Sometimes they'll add an R into the mix, which acts as a decimal point. So a 2R2 resistor is 2.2 ohms, and a 222 resistor is 2200 ohms. The hard part is usually reading the numbers because they are very small. This package size chart shows a lot of common packages. The names are pretty straightforward, with the first 2 digits indicating the length and the second 2 indicating the width. For example, an 0805 Imperial package is 0.08 by 0.05 inches, or 80 mil by 50 mil. When I'm choosing a package for a home project that I know I'm going to be soldering by hand, I'll usually choose 0805 resistors. The most common packages you'll run into are 0805, 0603, and 0402. If you're not able to tell what value a resistor is, you can always just measure it with a meter, but it's best to do this when it's removed from a circuit. If it's inside your circuit, other things can influence your measurement. Resistor power. Resistors are very efficient at turning electrical energy into heat energy. If you put too much power through a resistor, the magic smoke that makes it work escapes. To prevent that from happening, every resistor has a power rating. The most common power ratings you'll see are 1/4 and 1/8 watt, but there are much smaller and much larger power ratings available. Usually the power rating is directly proportional to the size of the resistor, with tiny surface mount resistors having ratings as low as 30 milliwatts or 1/32 of a watt, and large industrial resistors having ratings of hundreds or even thousands of watts. As long as you keep the average power dissipated in your resistor below its rating, the magic smoke will remain trapped forever and it will continue to work normally. There's an easy way to check that your design is safe. For any electrical component, the power dissipated is simply current times voltage, or P equals I times V. In a resistor, we can use Ohm's law to get 2 useful variants of the power equation. P equals I squared times R, and P equals V squared divided by R. All 3 equations can be useful when selecting resistors. In my first example circuit, we need to produce 10 milliamps of current from a 100 volt supply. We can do this with a resistor, but using P equals I times V, we know that the power consumed will be 100 times 10 milliamps, which is 1 watt of power. That means we'll need a pretty beefy resistor to handle this. In another example, we have a current sense resistor that's 10 milliohms, and we know our current can be up to 4 amps flowing through it. Using P equals I squared times R, we know that our power dissipated is 160 milliwatts, so we'll need at least a quarter watt resistor for this application. In my last example for the power section, when sizing a pull-up resistor, we know our supply voltage is 5 volts, and we want to use 8th watt resistors on our board, because that's what we have available. So we can use P equals V squared divided by R to quickly learn that our resistor must be larger than 200 ohms to work safely in this application. The power consumption of components is something that is often overlooked in designs and is also a common point of failure for prototypes. Make sure you are using appropriate power ratings and you won't have any issues. Well, at least from your resistors. Using resistors. There are times when you need to draw some current from a voltage source, and a resistor is a great way to achieve this. In this example, we have a 5 volt supply that needs to have at least 450 microamps drawn from it to maintain stability. I know I can do this with a resistor, but I need to calculate the correct value. I'll go ahead and add 10% to make sure we're drawing enough current so long as my resistor is within tolerance. Let's call it an even 500 microamps. I know the voltage is 5 volts and the current is 500 microamps. And those two values define the resistor's value using Ohm's law of the form R equals V divided by I, which gives me 10 kiloohms of resistance. Putting that resistance into the circuit and running my simulation, I can see that the current is 500 microamps, just like I expected. Just as a double check before we build this in the real world, I'll check the power dissipated in the resistor. With 5 volts and 500 microamps, we know that it will be 5 times 500 micro, which gives me 2.5 milliwatts, which is easily within the limits of my 8th watt resistors. Let's go ahead and build this on the bench and check that reality lines up with the simulation. Here I've got a breadboard set up with my load resistor connected between the two power rails on the board. The color bands are brown, black, orange, gold, which means I've got a 10 times 10 to the third, or 10 kiloohm resistor with a 5% tolerance. I have the supply disconnected so I can measure the value, and it looks like it's 9.92 kiloohms, which is actually less than 1% off the nominal value. Connecting up the supply, we can check the voltage. Remember that voltages are always measured between 2 points, and here I'm measuring directly across the resistor. 4.99 volts. Looks pretty good. Then we can switch over to current measurement mode, which turns my meter into a short circuit. To measure current, we put the meter in series with the load. I chose to put it on the ground side here, but it would have worked on either side. Looks like we have 0.49 milliamps. But my meter has a microamp mode that's a little more accurate, and I can see that it's actually 498 microamps, which is very close to what both our calculation and our simulation showed us. Let's move on to the next common application of resistors. Here we're using a resistor as a current measurement device. For the simulation, I've set up a current source of 10 milliamps, which is the maximum current I want to be able to measure with my shunt. I know that my measurement instrument can accurately read between 0 and 1 volt. So using 1 volt and 10 milliamps, I can go back to R equals V over I again and get that I need a 100 ohm resistor as my shunt. Running the simulation, we can see that the current through the resistor is being forced to 10 milliamps, and the voltage across it is 1 volt. Let's test this out in the real world. Here I've connected up my shunt resistor. Brown, black, brown tells me it's 100 ohms, and I've set it up to have both the current and voltage measured at the same time. On the left, I'm measuring the voltage across the resistor. On the right, I'm measuring the current through the resistor. As I increase the current forced through the resistor, you can see that the voltage across the resistor increases perfectly linearly and displays a value 100 times the current through the resistor. With 10 milliamps of current through the resistor, we can see exactly 1 volt across the resistor. As you can see, the current meter here is not really necessary at all. The voltage on the resistor will directly tell us what the current value is. Another application that puts a resistor in series with the load is a protection resistor. I've added a 1 kilo ohm resistor in series with a 5 volt supply. That resistor will allow me to still power low current loads, but it will protect the supply from higher current events such as short circuits. If I connect a 15 kilo ohm load, then the current drawn is only about 300 microamps. We do lose a little voltage over that 1 kilo ohm resistor, but most of the supply voltage still makes it to the load. If we replace that load with a diode, then the current jumps up significantly, but it still doesn't damage the supply. And even if we short out the load completely, we're only going to see 5 milliamps coming out of the supply because of the 1 kilo ohm resistor in series with it. Let's look at this on the bench. My protection resistor is in the upper corner of the breadboard, so anything I connect between the black and red wires will be in series with it. With no load, the voltage is 5 volts, as we'd expect. Adding a 15K resistor, we see the load voltage drop to 4.7 volts, with the remaining 300 millivolts showing up across our protection resistor. And of course, 300 millivolts across a 1K resistor tells us that there's a 300 microamp current flowing there. If we short out the load with a wire, we can see the current jump up to 5 milliamps, but it doesn't go any higher because the circuit is protected by our resistor. On to the next common use of resistors, a voltage divider. If you put two equal value resistors in series and connect them to a supply, the voltage between the two resistors will always be half of the supply. If your values are not the same, then it's a little bit more complicated, but not too bad. We know from Ohm's law that the voltage across the bottom resistor is just the current through the resistor times the resistor value. Let's keep this as a symbolic solution for now, and I'm going to call the voltage there the output voltage, or Vout, and that's equal to I times R2. We also know that we can combine two resistors in series by just adding them up, which gives us R1 plus R2 here. We can then use another form of Ohm's law, I equals V over R, to solve for the current through both resistors, which is I equals Vn divided by R1 plus R2. Going back to our first equation, we can plug in the value for I, and we get Vout equals Vn over R1 plus R2, and all that multiplied by R2. Or in the more commonly used form, Vout equals Vn times R2 over R1 plus R2. If we had, for example, a 2.5 volt input voltage, R1 as 10K and R2 as 15K, then we can plug the values into our voltage divider equation and find that the output voltage is 1.5 volts. Let's check that this really works. I put 2.5 volts across the pair of resistors, and you can see that across the 15K resistor there's 1.5 volt, and that's exactly what our simulation and equation predicted. One very common application of a voltage divider is to use a variable resistor to produce a user-selectable voltage. A potentiometer is typically a 3-terminal variable resistor. 2 of the terminals are connected permanently to the ends of a strip of resistive material, represented here in red. Those 2 terminals will always have the same resistance between them. The 3rd terminal is connected to a movable conductive wiper that contacts the resistive material somewhere in the middle. The resistance between that wiper and the 2 end terminals will vary depending on the position of the wiper. When it's turned all the way to one end, the resistance will be about 0 for the near terminal and the maximum for the far terminal. For my circuit, I'm applying 10 volts to the 2 outer terminals, producing a voltage divider inside the potentiometer. With the wiper near the top terminal, the maximum voltage is at the center terminal. At the center position, we'll see 5 volts. And as we approach the other end, the voltage goes to 0. Here's a real potentiometer, and I'm just going to be measuring the voltages around the circuit. You can see that I've placed a 10-volt supply across the outer terminals of the potentiometer, and the center terminal is measuring 5 volts, which means my wiper is in the middle position. Turning the wiper clockwise in this case reduces the voltage down all the way close to 0 volts. Turning the wiper back counterclockwise, we can see that voltage go up and up all the way to the supply of 10 volts. So the potentiometer is a really easy way to get a voltage anywhere from 0 to VCC that you can dial in by just turning the knob. So this brings us to the end of my introduction video for resistors. I hope that this video has been able to give you enough information for you to be able to effectively use resistors in your circuits. If you've made it to the end of this video, I'd like to say thank you very much for watching, and I hope that you have a great day.